Yesterday we did the simulation about the free throws. So we are going to skip down to this chart and sketch a graph of what the percentages made were given just a few trials versus many trials. So at the beginning, if we have a zero trial, so we're going to start with 0, 0. And then the way mine worked is like after 5 trials, I still had 100%. So I'm going to put like that. So it went kind of like this. And then around 10 trials, I was at 90%. But then 20 trials, I was at 80%. 30 trials, I was at like 85. And then 40, I was at 78. At 50 trials, I was at 81. 60 trials, I was right at 80. Well, I think if I rounded. And then 70 was 81. And 80 was like 79. And the claim was that she had an 80% shot record of free throws. So put a dotted line at 80. So what do you see over the long run where the probability is about? It's about 80. So our long run probability gets closer to the actual. But in the beginning, from here to here, this is kind of an unpredictable area. The first part. But then as we get more and more simulation, more and more trials, this becomes more predictable. And that's based on the law of large numbers. So from here to, just a few trials is kind of unpredictable. But once you get more and more trials, it becomes more and more predictable. Okay, turn to the next page. So that's your long run relative frequency. Relative frequency is your probability, which is between 0 and 1. In the short term, it's unpredictable. So like having a kid, half boy, half girl. But if you're just having a few kids, you can't just say, oh, they're going to have 1 and 1. It's not like that. The more kids that they have, the more likely it will be half and half. But you'd have to have a lot. And then so that's the long run probability. It becomes more and more predictable. So more and more trials, more and more samples, more and more simulations going to give you a more predictable outcome. And then the law of large numbers was the law we talked about yesterday. If we do something many, many times, the proportion of desired outcomes will approach its probability. So sometimes you need thousands of simulations. So that's why computer-generated simulations help us with that. Instead of going and doing the trial many, many times, you would do simulations to represent those. So let's talk about probability. I am going to use 0, 0.1, and then 0, 3, 6, 9, 9, and 1. So I'm just changing that one. Use 4 of the following probabilities to complete the middle column of the table. Then give an example of an event that may have this probability. So the first one is, this outcome is impossible. It can never occur. What would be the probability of an event that could never occur? 0. So what's a probability, or what's an example of something that could never happen? Let's talk about rolling a die. What could never happen when you roll a die? There you go. So rolling.
20-sided die. What was a 20-sided?
So we're going to be specific now. Rolling a 7 on a 6-sided die. Okay, what about an event that is absolutely certain? What is that probability?
It's already happened.
Not already happened. What would be the... Yeah, it'd be 1. It'd be the 1. It'll occur in every trial. So what will occur in every trial of rolling a 6-sided die? Getting 1 through 6, right? Rolling a number 1 through 6 on a 6-sided die. Die is singular, dice is plural. All right, the next one. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. What number would I use for that? 0.1. So let's make up a silly one. This outcome is very unlikely, but it'll occur every once in a while and long. So what would be an example of something?
2 sets of twins.
Huh?
2 sets of twins.
Yeah, sure. Missy Saucy making it to the WNBA. It's like 0.0001. But that was my dream whenever I was in middle school. I should have followed my dreams. Okay. What about having an outcome that will occur more often than not, but doesn't occur almost every time? 0.6. What's a silly example of that?
Dies are just kind of lame. We should do something real crazy next time.
Yeah. So what would be that would have a 0.6 chance? It's going to happen a lot, but not every time.
You get a 4.
Rolling 1 through 6 on that, like 10-sided die.
You get 4, 5, and 6.
Yeah.
Will that be? You get a 3, 4, 5, and 6.
Yeah.
It's a little bit more than 0.6.
So rolling 1 through 6 on a 10-sided die. In the last class, we were like, the 0.1 was having your order wrong at Chick-fil-A. Because they're usually pretty solid, Chick-fil-A is. And then the other one was having your order wrong at Whataburger. Right? Happens all the time. All right, number 2. In the Wheel of Fortune, there is a 1 in 9, which is 11.1% probability of spinning bankrupt on any given spin. Interpret this probability. So remember yesterday I gave y'all a template, like we're going to have to use this when we interpret a probability. So look at the previous page. It was number 4. If, I guess I put we or you. If you take a very large sample, What is our sample going to be? What are we going to simulate multiple times? Yeah, the wheel's fortune spins. So if you take a very large sample of spins, what are we going to see happen most of the time?
11.1% will land on bankrupt.
So we do want to put a little describer word in there that makes it like, it's not going to be exact. So we got to put the word about. About 11.1% will land on bankrupt. So then in 9 consecutive spins of Wheel of Fortune, none of the spins land on bankrupt. The next contestant worries that he is more likely to land on bankrupt now because bankrupt is due. Explain why this thinking is wrong.
It resets every time.
Probability is what? Doesn't change.
I just said it resets every time.
Yeah, it doesn't depend on anything else. It's independent, yes. So each spin is independent. The spin before it doesn't matter. You look at what the actual probability is. It's always a 1 in 9. All right, we're going to skip this one. And let's go here. Okay, a simulation, imitation of chance behavior based on a model that accurately reflects the simulation or the situation. Okay, example of devices. So we can use dice, but it has limits. You have to have 6 options. So 1 in 6 for dice. You can use a coin flip. 1 over 2. What else could we use to simulate some kind of situation, chance probability of anything? Yeah, random number generator.
The hat.
Yeah, the hat method. So for the RNG or hat method, if you say it has a 70% chance, then you would have to label something as yeses, something as nos. So for 70% chance, you do like, okay, 1 in 7 is going to represent a yes, while 8 through 10, because you need it 100%, right, is going to represent my no's, or whatever the situation is. Bankrupts, not bankrupts. So then you have to describe what each one means. All right, so there's a whole process. So you'll have to label each of these parts. So the simulation process, the first part is to describe one trial. So the way you do that is you label, then you randomize by using one of the devices, and then select and count. And then we have to do the law of large numbers, so we have to perform many trials. But you have to specify how many. And then use those results to answer the question. So on the AP exam, you won't be asked to do a simulation. You'll be asked to describe and then analyze some results that are given to you. So it says, some people have wondered if the Wheel of Fortune wheel is fair. If it is fair, the bankrupt result should occur with a probability of 1 out of 9. To test the wheel, Pat Sajak observed a random sample of 50 spins of the wheel and found that bankrupt was spun 10 times. Is this convincing evidence that bankrupt comes up more often than it should? Describe how you would carry out a simulation to estimate the probability in a will and then that bankrupt comes up 10 or more times. So he's wondering the question. So the question is the will fair? So we will carry out a simulation. So describe one trial is what we're going to do on part A. So number 1 is label. We've got to determine what's going to be considered bankrupt and what's going to be considered not bankrupt. So I'm going to use a random number generator on this one. So I'm going to say that 1 is going to be bankrupt. And then, so it's 1 out of the 9 are bankrupt. So that means I will do 2 through 9, not bankrupt. So that'll simulate what the actual is. And then I want to use the random number generator to generate numbers. And I only want the numbers 1 through 9. The ones that I'm concerned about are the ones that say bankrupt. So I'm just going to count the ones, the number of ones. And it looks like it says the dot plot displays the results of 100 simulated trials of 50 spins. So that means I'm going to do it 50 times, do a 50 spins. Because I'm just describing one of the trials. Then you repeat this trial 100 times. So repeat until 50 spins are simulated. So the simulation, one trial is 50 spins. They did this one trial 100 times, and here are the results. So we didn't have to find the results, so we're just going to analyze them. So part B says, explain what one dot above the 12 indicates. What does that 12 mean?
One trial of 50
One trial of 50 spins. In which what? In which, how many got bankrupt? 12 were bankrupt. That's a lot. So it happened one time in the simulation. So it says, what conclusion would you draw about 10 or more bankrupt spins occurring in 50 spins? So let's draw a line on our dot plot at the 10 or more. And we are going to write this as probability that x is greater than or equal to 10. For our 100 trials. So how many were 10 or more? 4 out of the 100. What percent of the time will they get that? Or did they get that? 4%. So yesterday we had like a mini look at if it's unusual or not. Well, today I'm going to give you a value to determine if it's unusual or not. 5% is considered unusual. So anything below that, it's unusual. So it's unusual to have 10 or more bankrupts in this situation. So compare to, actually I'm going to use it as a decimal. P equals 0.05. That is our boundary point. So if it's smaller than that, it's considered unusual. We'll probably see that later. I don't know if it's less than or just less than or equal to. I'll have to look that up. So smaller than 0.05 is considered unusual. So C is going to be our conclusion. So it's going to be a little bit, we got to write a little bit. So write small. So it says, what conclusion would you draw about 10 or more bankrupt spins occurring in 50 spins? Explain your answer. So assuming the will is fair, there is about a 4% chance of getting 10 or more bankrupts. Out of 50 spins. Since 4% is less than 5%, this is convincing evidence that the will is unfair.